This video, let us focus on some problems from optics. So here we have a question from thin film. The condition for constructive interference in thin film is 2nt 2nt cos theta t is equal to m plus 1 by 2 lambda. This is the condition when there is only one phase shift. And if there are two phase shifts, then the condition is 2nt cos theta t is equal to m lambda. This is the case when there are two phase shifts. This is the condition for constructive interference in a thin film. Here n is the refractive index, n is the refractive index, t is the thickness of the thin film, theta t is the angle of refraction inside the thin film, and lambda is the wavelength of light in vacuum. Now you may be confused where one phase shift occurs and where two phase shift occurs. So let me briefly introduce that to you. So this is our film of refractive index, let's say n, and this is air, refractive index is n1, and this is also air. Both sides are surrounded by air. Let's say if n1 is less than n, then at this interface the light is reflected from a higher refractive index, but at this interface the light is reflected from a lower refractive index. So the condition for a phase shift of 180 degree to occur is that when light reflects from a medium with a higher refractive index, then it undergoes a phase shift. So in this case there is only one phase shift. Because only at this interface there is a reflection from a higher refractive index. Here we have n1 is less than n, so there is no phase shift occurring here. Now consider another case where we have a situation like this. Here is a medium with n1 refractive index, this is film with refractive index n2, and here is another medium with refractive index n3, and we are told that n1 is less than n2 is less than n3. So in this case, here also there will be a phase shift occurring, and at this interface also, at this interface as well we have a phase shift, because both the reflection are occurring at higher refractive index. So in this problem, since we are told that the thin film is surrounded by air on both sides, So only one phase shift occurs, so we will use this condition. We will use this condition. So 2nt cos theta t is equal to m plus 1 by 2 lambda. Now n is given, n is equal to 1.4, t is equal to t is to be found out. T is to be found. Theta t is equal to, it is said that the light is incident perpendicular to the surface, which means theta I is equal to 0, and from Snell's law n1 sin theta I is equal to n sin theta t. So this implies theta t equal to 0 as well. So theta t is 0. This implies cos theta t equal to 1. Therefore our condition simplifies to 2nt equal to m plus 1 by 2 lambda. For minimum thickness, we are asked to find minimum thickness. M is equal to 0. M equal to 0 for minimum thickness. This implies 2nt equal to lambda by 2. Now you substitute the values. 2 into 1.4 t equal to lambda is 400 nm by 2. This implies t equal to 400 nm by 4 into 1.4. This turns out to be approximately 70 nm. But the correct answer that is given in answer key is 140 nm. So I don't know why it is 140. For me, the correct answer is 70 nm. Here we have a question from JEST 2023. There is a light of intensity I0. It is passing through this optical system, which consists of 4 beam splitters, and each of these beam splitters are 50-50 beam splitters, which means they reflects 50% and transmits 50%. So initially we have I0 is equal to 120 watt per meter square. Now this, after going through BS1, beam splitter 1, it is split into 2. So its intensity is reduced to half. The half portion is reflected and half portion is transmitted. So that means I1 is equal to 60 watt per meter square, and the remaining 50% that is transmitted through here. So this is 60 watt per meter square. Now that light reflects from here and transmits. So I2 is equal to 50% of 60 watt per meter square, that is 30 watt per meter square. And the light which is going to BS3 has intensity 30 watt per meter square. After reaching at beam splitter 3, it is reflected 50%, transmitted 50%. That means I3 is equal to 50% of 30 is 15 watt per meter square. The remaining 15 is reflected, so this is also 15 watt per meter square. This again 50% is reflected, 50% is transmitted, so that means I4 is equal to 7.5 watt per meter square, and the remaining 7.5 is reflected, so this is 7.5 watt per meter square. Now after one cycle it again comes back to beam splitter 1. Now this 7.5, it again 50% is reflected, 50% is transmitted. So I1 is equal to 60 plus 7.5 by 2. And here also the transmitted part, the reflected part, it will add, so 60 plus 7.5 by 2. Now this 7.5 by 2, it again 50% is reflected, 50% is transmitted, so that adds to this as well. So 30 plus 7.5 by 4. Here I2 is equal to 30 plus 7.5 by 4. Now this 7.5 by 4, it again reflects and transmits after reaching BS3. So we have I3 is equal to 15 plus 7.5 by 8 watt per meter square. Now after undergoing the next cycle, it will, some small quantity will again add to this I3, and it will be approximately, we can approximate that to 16 watt per meter square. So I3 value is equal to 16 watt per meter square. The correct option here is option C. The reason why I approximated the answer to 16 is because here we have a 15, here we have a 15, here we have 7.5 by 8, which is around 0.9, and the other quantities which is added in the third cycle and fourth cycle, they are very much less than 1. So we can approximate this I3 to be equal to 16 watt per meter square. By the way, the question that we solved earlier, this question was from JEST 2022. I don't find any reason for the answer to be 140 nm. If you have any other thoughts, you can comment. Let's move on to the next question. So this is from JEST 2021. Here we are asked to find the focal length of the lens. Since we are dealing with a glass sphere, it can be treated as a thick sphere, and we can use thick lens formula. So thick lens formula is one by f is equal to n minus 1 into 1 by r1 minus 1 by r2 plus n minus 1 into d divided by n r1 r2. Here r1 is the radius of curvature of the first surface, r2 is the radius of curvature of the second surface, n is the refractive index of the lens material, d is the thickness of the lens. So to find r1, we can draw the sphere. So this is our sphere, and light is coming from here. So there is a convention of choosing radius of curvature positive or negative. R is positive if surface is convex. Convex means curving outward. Curving outward when viewed from the incident light side. From the incident light side. R is negative if surface is concave, if surface is concave, that is curving inward, when viewed from the incident light side. So light is incident from this side, and you can see the first surface, which is this surface, it is convex, it is curving outward. So that means R1 is equal to positive and its value is plus R. And for the second surface, this surface right here, it is concave when viewed from the incident light side. So this is R2 is equal to, R2 value is, this is R with a negative sign, because when viewed from the incident light side, the surface is concave. So that's why R2 is equal to minus R. And D, the thickness of the lens material, the thickness of the sphere is 2R diameter, and refractive index is given to be N. N is the refractive index of the lens material. So if we put all these values in the thick lens formula, we get one by F is equal to N minus 1 into 1 by R1. R1 is plus R minus 1 by R2. R2 is minus R plus N minus 1 D. Thickness is 2R divided by N into R1 is plus R into minus R, R2. So this is equal to N minus 1 into 2 by R plus 2 into N minus 1 divided by NR with a negative sign. So this is equal to N minus 1 into 2NR minus 2NR plus 2R divided by NR square. This cancels. So 1 by F is equal to 2 divided by NR into N minus 1, or F is equal to NR divided by 2 into N minus 1. So this is the correct answer. Focal length is NR divided by 2 into N minus 1. Option B is the correct one here.